Till now, we have learned that locks are an important part of implementing the concurrency in Java. But we also need to have some sort of interaction between the threads and locks. So the mechanism which helps us in managing these interactions is called as condition. Let's understand what are conditions with a very simple and easy to understand explanation. Here I would request you to make a very weird assumption which could help in avoiding any confusion with the terminology of lock. Assume that lock here is the key as well. What I mean to say is, when you have access to the lock, the door which is guarding the protected resource is unlocked magically, and thus the lock is a key as well in that context. Hence, as soon as you acquire the lock, you get access to the resource. Please note that only one person is allowed to access the resource. No one else can tailgate behind you. With this in place, let's learn further. A lock in Java can have its own set of rules. These rules are called as conditions. Effectively, this means that a lock could have more than one condition associated with it. Conditions help us in controlling how threads interact with the lock. You could visualize threads as people who are trying to access some protected resource, and think of condition as a waiting room attached to the lock. Imagine a person comes up and tries to get hold of the lock, but lock is being held by some other person. Thus, this guy won't be able to acquire the lock. So what he does instead is he goes to wait in this room where other people may also be waiting for the lock to be available. Inside the waiting room, people wait until someone signals that it's their turn to use the lock now. This signal could come from a person that is currently holding the lock or from some other source. So, who gets the chance to acquire the lock? Well, that's something which depends on the implementation. The key takeaway from here is that after a signal is given, any one person from the waiting room is allowed to acquire the lock and do their processing. In Java, these conditions help in managing the interaction between threads and locks. Now, let's visualize how conditions work. Imagine there are two threads, thread 1 and thread 2. To begin with, thread 1 is executing something. However, it cannot move forward until some particular condition is met. This condition could be anything based on your use case. For example, a queue being full could be a condition. In this case, as soon as the thread cannot move forward, it will call condition.await. If you read this from the right, it appears as if a thread is saying that I am waiting for this condition to be fulfilled. So, I am awaiting for a given condition. Effectively, the thread 1 goes to a waiting state. Now let's imagine there is another thread, thread 2, and this thread is running and doing some operations. Due to the operations being performed, the condition gets fulfilled, and as soon as the condition gets fulfilled, this thread 2 calls condition.signal. It signifies that the condition has been fulfilled, so convey this message to any of the threads which have been waiting for this condition to get fulfilled. As soon as the signaling happens, JVM finds all the threads which are in the wait state anticipating this condition to be fulfilled and wake the one which has been waiting the longest. In this example, there is only one thread which is thread 1. So the state for thread 1 goes from wait state to the runnable state. So the thread 1 which was blocked at this point of time is now active from this point of time, because at this point of time thread 2 signals that the condition for which thread 1 was waiting, it has now been fulfilled. So thread 1 could proceed with its processing. Now let's analyze this scenario where we call condition.signalAll. Like we had condition.signal, there is another method signalAll. So in this example, we have three threads, and during its execution, thread 1 calls .await, and after some time, thread 2 also calls .await. There is another thread which is thread 3, and during its execution, the condition for which thread 1 and thread 2 are waiting gets fulfilled. So the thread 3 calls condition.signalAll. As soon as signalAll is called, all the threads which are waiting for the condition to be fulfilled are waked up by the JVM. JVM pulls them out of the blocked state and moves them to the runnable state. So depending on the number of cores your CPU has, threads could be scheduled for execution accordingly. So if .signal was called instead of signal all, thread 1 would have been waken up, since it's the one which has been waiting for the longest. So this is the way in which condition helps us into maintaining or managing the interaction between the threads and the locks. There are two methods, that is signal and signal all, which are used to notify that a particular condition has been fulfilled, and there is one method which is condition.await, which is used to hint that a condition needs to be fulfilled before a given thread could proceed further in its execution. In case if you are wondering that condition methods discussed above are very similar to the wait and notify methods in the object class, you are correct. Indeed, these methods are similar to wait and notify. The main difference, however, is that conditions provide a much granular control over the synchronization of the protected resource. Now, with that in place, let's have a quick code demonstration which will teach us how can we use the conditions and its related methods. Let's create a package and we can call this as locks, and let's create a class, call this as condition demo, and here is what we are going to build. So basically we are going to build a producer consumer implementation using the locks and conditions. So let's start. So first thing that we will have is a max size, which is the number of elements that could be kept in a buffer, which is going to be a queue. So let's have that. So it would be private final integer max size. Let's have the value as 5. The next thing is we will define the lock. So lock, and the type of lock that we are going to use is reentrant lock. So reentrant lock is one type of lock in Java. We will have to create the queue or the buffer where we are going to place the elements. So let's create the queue. Let's call this as buffer, and this could be of type linked list. So basically from this buffer, the consumer will be consuming and the producer will be writing to it. Next, we will be creating certain conditions. One condition would be that buffer not full, and the other condition is buffer not empty. So let's create the same. So private final, this is condition, and buffer not full lock. The way to create the condition is to call the .new condition method, and we will do the same for the other condition as well. So this condition could be something like buffer not empty, and we could have lock.new condition. So we will have two methods. The first one is producer. So private void produce and int item. So let's have this, and so what we will be implementing is the produce section of the implementation, and we want this to be synchronized. While this particular code block is getting executed, we don't want something else, or let's say some other thread, to come and work on this simultaneously. So the order to do this is, first we will have to acquire the lock, and the way to do this in Java is called log.lock. And once we are done with our processing, finally we need to call log.unlock. So this looks fine, but there is a problem. Let's say when the processing is under the way, there is some exception which happened. So in that case, the code will terminate then and there itself, right? The log.unlock will be never executed, and the other threads which are waiting for this lock will go into a state of deadlock, and that is not good. So the way to do this is call this log.unlock in the finally section or the finally block. So in either case, this log.unlock is always executed. So this is a common pattern which we use while making use of the locks in Java, and this is the way to implement this. So let's have the try block, and here we will put the processing, right? And we will have a finally block, and that is where we call the lock.unlock. So with this in place, let's implement the processing part. So here is what we are going to implement now. First we will check if the buffer is totally full. Then for that duration, we will have to make the producer thread wait. Otherwise, we will put some item in the queue and then we will notify if there is any consumer thread which is waiting for the producer to put certain item in the queue. So let's implement this. So we start by checking if the buffer size is equal to the max size, which is 5. If that is the case, then we have buffer not full, and on this condition this thread will wait. After that, we will add certain item to the buffer, and next we will have a print message which says something like produced, and produce this particular item. And for the buffer not empty, we are going to put the signal. So let's also complete the consumer method, then we can have a complete look over the entire implementation. So let's have private void consume, and like the produce method, it's also going to throw an interrupted exception. So let's have that in the method signature. We start by acquiring the lock, so lock.lock, and we will follow the same pattern that we saw earlier, that we will have a try and finally block, and in the finally we call the unlock method, and in the try we have the implementation. So here we will check if the buffer is empty, and if it's empty, then we call buffer not empty and await on this condition. And if this is not the case, then we are going to consume from the buffer. And the way we do this is we print a message which says consumed, and from the buffer we take out the element by calling the dot pole, and next we call a signal on the buffer not full. So this is the consumer method. So you may have a doubt here. What you may think is that the nomenclature of buffer not full and buffer not empty is kind of misleading and confusing. So I totally understand that, and I also had this confusion for quite some time. But the way to interpret this is that this nomenclature should be understood from the perspective of this signal. So the condition is buffer not empty. So what it means is that this buffer not empty condition is being awaited by certain thread. And which thread may await this? The thread which may await this is this one, right? That is going to consume. So if it's consuming, then at that point of time it needs to have something in the buffer, otherwise there is nothing to consume. So that is the reason if the buffer is empty, then on this particular condition this consume method is going to wait. And let's say if it's waiting for something to be put in the buffer, and then the producer method is executed by some thread, the producer thread, then at that point of time something was put in the buffer, some item was put in the buffer, and that is where once we have put something in the buffer, we are going to call this signal. So what essentially we are saying is that buffer not empty condition is going to signify that something needs to be there in the queue for the consumer to consume. And that is the reason consumer is going to wait on this condition, that is buffer not empty. Likewise, we have buffer not full. So buffer not full is being signaled by the consumer, and the idea remains the same, right? So when producer is producing something, then it needs to ensure that the buffer is not full, and if it's full, then it will have to await. And this condition is being signaled by the consumer, and what it means is once the consumer has consumed something, then there is certain space in the queue in the buffer in which the producer could produce. So that is the reason if there is a producer which is waiting for this condition, then this particular thread, the producer thread, will be awakened when this buffer not full is signaled. So that is the idea, and that is the intention behind this nomenclature and behind this implementation. Now let's complete this by writing the main method, and then we will have a code demonstration by running the code. So let's implement the main method, and let's have the condition demo object created. So new condition demo, right? And let's have the producer thread. Let's call this as producer thread, and let's have a try block and have a catch block as well. So when we call producer, it's going to throw that interrupt exception, so that is the reason we need to have it. And we are also going to introduce some sort of sleep, so that will be handled by the catch block itself. So what we are going to do is we are going to run this producer thread for 10 times, and we call the demo dot produce and pass I in this one. So I is the item that needs to be put. So essentially this producer thread is going to put 10 items in the queue, in the buffer. Next, let's have the thread dot sleep, maybe for 1 second, and in the catch we have a runtime exception, which is this E. So this should be for the producer thread, and for the consumer thread, let's have another one. First, let me rename this one to consumer thread, and again we will have the similar pattern. We will have a try and catch. Let's have the interrupted exception, and let's throw the runtime exception. And what we do is we are going to call consume 10 times. So I less than 10 and demo dot consume, and we are going to put a sleep for, let's say, 2 seconds. And once we have this thread created, we will have to call the dot run on these two threads. So first is producer thread dot start, then consumer thread dot start. So that should be it from the entire implementation perspective. Now let's run this and see the output. So you see, we have a demonstration, a simulation of the producer consumer problem. So produced 0, consumed 0, produced 1, consumed 1, and produced 2, produced 3. So remember, we had put a sleep timer of 1 second in the produce method and 2 seconds in the consume method. So in that sense, consume method is on the slower side, and that is the reason here we have the producer producing something twice, and consumer is kind of on the slower side. So we are producing twice and consumer is going to consume something once, right? But this pattern is not something which is very deterministic. The entire idea behind having that sleep was just to showcase the demonstration in somewhat presentable manner, right? So that should be it for the conditions in Java. And please note that these conditions could be only derived from the lock interface implementations, which are intent lock, read write lock, and any other implementations which you could explore in the JDK. And these conditions are not available for the locks that we have on the object level, the implicit locks which are available with the object in Java.